what is the vector operation that is going to help us find this distance from the ship to the base of the track? Because it doesn't matter where the ship is, right? Left or right here. We need all we need is always this distance from the ship to the base, from the ship to the base, from the ship to the base. Look, if you ever studied game physics with me, or if you ever studied even 3D graphics with me, vectors and vector operations, they are everywhere, right? We should have that under our skin already. Vectors are super important tools for programmers, especially game developers, especially 3D programmers, right? In my time, whenever I was a graphics programmer, my God, it was vectors every day. It was vectors, right? So think about this. If we have these two vectors, super important, right? The normal of the section and this vector that goes from the base of the track until the position here of the ship, I have a vector operation which can help us project this thing right here onto this vector. So it helps us project this vector blue onto the normal vector. So it's going to give us this value right here. So this is what we're actually looking for, right? Is the kind of a projection of this blue vector onto the magenta 1 normal. And this is going to give us this lime green quantity right here. Do you agree that this is the distance that we want, the height from the ship until the base? And this thing right here is a vector operation that we call the dot product. So let me just quickly review what the dot product is all about. So, given that we have two vectors, there is one vector operation called the vector dot product, which is going to give us exactly that projection of one vector onto another. So for the sake of simplicity, imagine that this vector A right here is a unit vector, has the length 1, right? It is, in other words, a normalized vector. Given that this thing is a normalized vector, we have an operation that is going to project this vector B onto vector A, and is going to give us this thing right here. So this projection of B onto A, this is going to give us this value, right? A dot B, but just pay attention that this is not another vector. This is a scalar value. So one of the first rules that you probably, right, if you ever study with me, you were tired of hearing, is that dot product returns for us a scalar value. It is a number, right? So this number right here is how much B is projected onto A. And that has everything to do with what we want, right? We want to kind of project that blue vector onto the normal of the section, and that is going to give us the kind of the height of where the ship is with relationship to the base of the track, that base vertex that we have. So just for the sake of completeness, A dot B, mathematically, right, we have it comes from the first vector x times the second vector x, so the first x times the second x, plus the first y times the second y. So it's x's times x's plus y's times y's. And also, right, if we have now a third component is z's times z's, because this I'm looking at 2D, but we're going to have the 3D version of this, which is going to be exactly that, right? So x's times x's plus y's times y's plus z's times z's. If I perform this multiplication plus this multiplication plus this multiplication, this is going to give us a number, a scalar value, which means how much this thing is projected onto this thing. You will also see that people talk about, right, this projection. It has everything to do with how aligned these two vectors are. So if B is perfectly aligned with A, it projects 100%. If B is 90 degrees perpendicular to A, it doesn't project anything. The dot product is 0, right? And if it is unaligned, then we go into the negative dot product. So positive dot product, 0 dot product when it's 90 degrees, and then negative dot product when these things are not aligned. Again, what we are really interested in is this projection, right? Is thinking about the dot product as this projection of one vector onto another, which, if we come back here to our problem statement, look at that projection, right? So think that this vector right here was our B, the normal vector, and we want to project this vector B right here onto that normal vector. And it doesn't matter if this thing right here is going to surpass the length of n, it's going to give us this magnitude right here, which is a value. And I am going to call this value, right, the return, the result of the dot product, I'm going to call this the height that I'm looking for. It can be height, it can be distance. I'm just going to call it height because it makes sense, right? This height right here is the height between the ship and the base of the track that I'm looking at. This lime green value right here. And why are we talking about this height? Because the strength, the magnitude of this force up or force down, we need to consider how far we are from the base of the track, right? Because if I am going too much close to the track, I need to increase the force up to repel the ship based on the height, right? So the bigger the height, the less I have to push up. The shorter the height, the more I have to repel. Do you see where we're going with that? So, given that we have a normal vector of the section, given that we have the height between the base of the track and the ship, right? Regardless of where the ship is, here left, right, we're going to have this height, this projection, which is going to give us this scalar right here. How do I think about the strength of, or the magnitude of the force down? Well, the force down is almost like this kind of force of gravity that is kind of pulling my ship down. So what I think I'm going to end up with is, my force down is going to be, the direction of the force down is minus normal, right? So we all agree that it is the flipped normal pointing down. So minus normal times, and I'm calling this thing k pole. This k is a constant. It is going to be a scalar constant value, which is going to be a magnitude of how much I want to pull down. And we're going to have to find this k constant value, right? We're going to have to play with the numbers and see how much we want to pull down based on that. But now that we are pulling our ship down, we have to compute how much we are going to push our ship up. And how much we're going to push our ship up has to do with this force that is already pulling down, plus how high we are compared to the base of the track. So my force up strength magnitude, I think, is going to come up from, is going to be in the direction of the normal, so in this direction up of the normal, times another, what I'm calling k push, which is going to be a constant push value, right? So how much we have to push up. But then look at what I'm doing. I'm dividing by that height value that I computed from the dot product, right? So this height right here. And I wanted to already look beyond the formula and try to understand what the formula is telling us. Look at this. My force up, the magnitude of that force up, or how much I have to push up the ship, has to do with the height of where I am in height from the base of the track. Do you agree that if I am on a bigger height, the higher I am, the less I have to push up, and the closer I am, so the shorter the height, the more I have to repel and push up? This is an inversely proportional relationship. That is why we have the height on the denominator of this fraction. The bigger the height, the smaller the force up. The smaller the height, the bigger is the magnitude of the force up. All right, so inversely proportional. And I wanted to think again, pause and think what this is telling us, right? If you are high on the track, you don't have to push up that much. But if you are very close to the track and the height is small, then you have to really push up and repel that thing, right? Repel the ship so it doesn't touch the track, right? Inversely proportional relationship. So I just wanted to think about these things and why I'm kind of already telling you these formulas and this high-level overview of how we're going to compute the magnitude of the force down and the force up, right? Cool, so now that we have the direction of these forces and the intensity, right, and the height plays a part on how much we're going to repel from the track, I think there's nothing left for us to do but to translate this into code, right? Because we have to compute the dot product, we have to compute this force up, force down. So let's just quickly go now in the next lecture. Let's just go back to our code editor and let's just translate all this logic that we discussed into code, right? And hopefully we're going to see these two forces playing a part on how much we repel or attract the ship to the track that we are playing in our game level.